Good morning, students. The topic of today is recursion. What do you understand by recursion? The process in which a function calls itself directly or indirectly is called as recursion, and the corresponding function is called as recursive function. Using recursive algorithms, certain problems can be solved quite easily. For example, the problem of Tower of Hanoi, in-order, pre-order, post-order tree traversal, and depth-first search of the graph. A recursive function is defined as follows. Suppose f is a function containing either a call statement to itself or a call statement to a second function that may eventually result in a call statement back to the original function, then f is called as a recursive function. The recursive function must have the following two properties. There must be a certain criteria called as the base criteria for which the function does not call itself. Each time the function does call itself, it must be closer to the base criteria. The idea behind the recursion is to solve some problems that can be broken down into smaller versions of the same problem. For example, consider the example of factorial. For example, we are taking n factorial. N factorial is equal to n into n minus 1 factorial into n minus 2 factorial up to 3 to 1. The factorial problem can be solved using another approach. Factorial function can be defined mathematically as follows. If n is equal to 0, then n factorial is equal to 1. If n is greater than 0, then n factorial is equal to n into n minus 1 factorial. Observe the definition of n factorial. It is recursive since it refers to itself when it uses n minus 1 factorial. Here, n is equal to 0 is called as the base condition. The example of recursion of factorial function is explained in next slide. Here, 5 factorial is equal to 5 into 4 factorial, where 4 factorial is equal to 4 into 3 factorial, 3 factorial is equal to 3 into 2 factorial, 2 factorial is 1 into 1 factorial, and 1 factorial is equal to 1. Here, this is called as the base condition, which we always need as a terminating condition to end the recursive function. Now, let us consider the second example of Fibonacci series. We all know that in Fibonacci series, the sum of previous two terms is the next term. The terms in the Fibonacci series are 0, 1, 1, 2, 3 up to so on. Fibonacci series is defined recursively as follows. If n is equal to 0 or n is equal to 1, then fib of n is equal to n. If n is greater than 1, then fib of n is equal to fib of n minus 1 plus fib of n minus 2. This is another example of recursive definition since the definition refers to itself when it uses fib of n minus 1 and fib of n minus 2. Here, the base values are 0 and 1. This can be explained diagrammatically as follows. For example, consider if we want to calculate the fourth term of the Fibonacci series, it is the sum of the previous two terms, fib of 3 and fib of 2. Then, which are again, fib of 3 is again the sum of fib of 2 and fib of 1. Whereas fib of 2 is again the sum of fib of 1 and 0. When we reaches the base conditions, fib of 1 and fib of 0, then we stop and we retract back to find the value of fib of 4. This is how the Fibonacci series is calculated. The terms of Fibonacci series are calculated recursively. This is how the recursion works. Thank you.